All right, let's get this show on the road. Hello, everyone. Hope you're well. Welcome to another edition of Math 1207. We're already starting a bit late, so let's jump right into it. Let me share everything here. Okay, so hopefully you guys are doing okay. I'm a bit frazzled, back-to-back meetings and classes today, but let us forge ahead. So as I mentioned, tomorrow you guys do not have a quiz, so you don't have to worry about that. But I would encourage you to talk about things on the first test that you didn't understand, as well as things about series that you don't understand. So your quiz next week will cover everything we've spoken about with sequences and series, including what we're going to talk about next week. As you're probably aware, next Tuesday, there are no classes because it's election day, so you guys can go out and vote if you so desire and you're available. Definitely do that. But yeah, on Monday, we're going to continue. Let's see how far we get today. But let's do a quick recap before we jump in. So we've been talking about series, and for us, series really means infinite series. We want to know how to add up an infinite number of things efficiently and see when this gives us a finite answer or meaningful answer. And knowing to what these things add up is very difficult, and so we have tests that can tell us whether or not these infinite series will converge, quote unquote. That means they add up to some finite real number, something meaningful we can interpret. And so these were the series convergence tests. And last class, I actually finished the table with you. So now we've gone once over every series convergence test there is. So a very important table here. And today I'll actually be talking a little bit more about how to actually use this table. But we went over each of these tests to talk about when a series might converge. What I do want to put more emphasis on to start out with, though, is this idea, the idea of absolute convergence, what I asterisked last time. Because as you know, when a series converges absolutely versus conditionally, it has all sorts of consequences for the mathematics and the analysis that we want to do with that series moving forward. And so we do want to, it's very often that we want to actually determine whether or not a series converges for one, but does it converge absolutely or does it converge conditionally? This is a very common thing. And this will be a question that I will be asking you guys directly. So there are times when I will give you a series or a bunch of series, and I won't even just say, do they converge? I'll ask you to specify, do they converge absolutely? Do they converge conditionally? What is the kind of convergence? Or do they diverge altogether, right? And so that's where we are right now. And everything you need to know about that is actually in this table, and there are some examples here that we're going to go over, but it all begins with this table. So there's a certain process that we'd want to go through to make sure that we're not missing anything, and that's in this table right here. Okay, there we go. Okay, so you can even take care of that, take a screenshot of that picture. Because we are going to be referring to it in the examples following. Okay, so at this point, we understand the idea of what it means to converge and whether or not we can test that something is converging and the methods that we can use to test whether or not a series is converging. Now we're going to answer the question, how can we tell whether the convergence is absolute or conditional? And it's not anything new, really. We are going to be using the same old convergence test that we've been using. However, we're going to be using these tests within an overall strategy, where the strategy is geared towards determining the type of convergence. Okay, so suppose you are given a series AN, and you're asked whether it converges absolutely, converges conditionally, or diverges. First thing, step 0, that you want to do is make sure that it doesn't obviously diverge. This is not only true in this process, but that's true in almost every time you approach a series and you want to determine whether or not it converges. You always want to check the test for divergence to make sure that it's not just an obviously it's not going to have an answer kind of thing, right? This step involves you just taking a limit, so it should be quick for you to actually figure out whether or not it will give you any definite conclusion. So you always just check in the beginning, right? So step 0, you apply the test for divergence. If the series is found to diverge from the test for divergence, then you stop. You don't have to do anything else. You stop the process and you say, the series diverges, right? So I can give you a series and I can say, does it converge absolutely? Does it converge conditionally? Does it diverge? If you hit it with the test for divergence and that says it diverges, then it diverges, right? It doesn't have any kind of convergence. You just stop, right? And so you get away without having to apply any series test. So that can save you a lot of time. So that is like step 0. Okay. So let's assume that the test for divergence is inconclusive, meaning that the limit was 0. So we don't know for sure whether or not it diverges. So that's what when you move on to step 1, right? So as you can see there in the table in green, I said, okay, if it's found to diverge, you stop. If it's inconclusive, move to step 1. So now we're in step 1. You will check absolute convergence first. There are a couple reasons for this. One, absolute convergence is the more important kind of convergence, right? So that's the one that you're really interested in if it converges absolutely. Another thing is, if something converges absolutely, it will automatically converge conditionally, however, not the other way around, which means if you check conditional convergence first, then you would also have to check absolute convergence because it might also converge absolutely, but checking for conditional convergence is not going to tell you that. However, if you check absolute convergence and you find that it does converge absolutely, it means that it automatically converges conditionally. You don't even have to check it. So you're again in a position where you have to do the least amount of work. And so you hit it with the test for divergence, make sure it doesn't obviously diverge. Then if that is inconclusive, you moved on and check absolute convergence, right? You check absolute convergence, remember, just by putting absolute values around sequence terms. And then you'd get a new sequence probably, right? If they're positive in the first place, you'll get the old sequence back, series back. But potentially you get a new series, right? Then what do is you hit that series with one of the convergence tests that I told you about as of last class, right? So you're going to hit that, you're going to test that with absolute values around it to see if it converges. And if it converges at this point, then you stop. Your conclusion would be the series converges absolutely by whatever test you use, right? So you can throw absolute values around it, and then you decide to, hey, let me hit it with the integral test and see what it says. And the integral test would tell you that, okay, with absolute values, it's going to converge. Then your conclusion would be the series converges absolutely by the integral test. You can just let them know that you use the integral test to check it, okay? And so that is how you go about that, right? Now, let's suppose you put absolute values around all the terms, you hit it with a convergence test, and the convergence test tells you that it diverges. It turns out that you cannot conclude from this that it diverges altogether because it might converge without the absolute values, right? This is called conditional convergence. So this moves you down to step 2, okay? So with step 2, what you're going to do is you're going to remove the absolute values, and then you're going to hit it with some other convergence test and see, can you get it to converge now, right? And at this point, you would have gone through all the possibilities. You would be able to, at this point, make a final conclusion. If after this last-ditch effort, it diverged, then you can say the series diverges in general. If after this point, you found convergence, then you would conclude the series converges conditionally by whatever test you use, okay? So that is the strategy overall in a nutshell. We're still using the convergence test that I mentioned that we've been going through over the last 2 classes. However, we're using it in an overall schema where we can tell what kind of convergence we're experiencing. So I give you a series, again, just to say it short and sweet. I give you a series and ask you, does the series converge absolutely? Does it converge conditionally? Or does it diverge? Step 0, hit it with test for divergence. If it diverges, stop and say the series diverges. If it's inconclusive, move on to step 2. Step 2, step 1, check for absolute convergence. Put absolute values around it, hit it with one of the convergence tests, see if it converges. If it does converge, you stop, say it converges absolutely. If it doesn't converge, move on to step 2. Step 2, remove the absolute values and hit it with a convergence test again. Does it converge now? If yes, you can conclude it converges conditionally. If no, the conclusion is the series diverges. There's no kinds of convergence, it all diverges. Okay? So that is the overall strategy. There was a comment here. Okay, so that's what we're doing. Okay, so now I'm going to illustrate this process with you guys by going through these examples. And I don't know, hopefully you guys tried it before. But we're going to work through this. Okay. So here's the problem, and this is how it would be phrased on like a test or a quiz or something like that. And a test, the justification part is going to be important. Determine with justification whether the following series converge absolutely, converge conditionally, or diverges. Once the problem is phrased that way, you know you have to go through the process that I highlighted just above. Okay? So when you're doing this, you always run in with step 0, test for divergence. First thing, okay, what does that mean? Well, I'm going to take the limit of the AN term, right? And it's always n goes to infinity. So yes, sometimes I'll be lazy and I won't even write the n goes to infinity because it's understood, right? So what is that limit?
0.
It's 0. Okay, so what does that tell us?
It converges, or it doesn't diverge.
We know it doesn't. No, we don't know that either, actually. No conclusion. It's inconclusive. Watch out for that, though. That is a common misconception. Even sometimes when someone would say that to themselves, I know it doesn't mean converge. I know it doesn't mean converge. I know it doesn't mean converge. They would go into a test and they would see the 0 and conclude that it converges. Like, it's very sneaky. Your brain just wants to tell you that, oh, if it converges to 0, it's going to converge, right? Not true, right? So if we had the 1 over n, it goes to 0 and it diverges. If it has 1 over n squared, it goes to 0, but it converges. You cannot make any conclusion based on 0. You can only make a conclusion based on the non-zero output. If it's not 0, I know for sure it diverges. All other cases, I don't know. If it's 0, I don't know. It could not. It's completely inconclusive. Okay, so test for divergence, I couldn't get out of it, so I'll move on to step 1. So here I'm going to check absolute convergence. What does that mean? It means I literally go to the series and I put absolute values around it, around the terms. So this is cosine squared n plus 1 over n squared plus 1. And now I'm going to ask myself the question, does this converge? Okay, what do you guys think? What could I do here?
I have a question really quickly about this series. So we were making like partial sums of this series, then would this be in degrees or in radians, or would it not really matter?
It wouldn't really matter.
Okay.
I mean, your n is going off to infinity, right? I mean, when your angle is going off to infinity, like if it's in degrees or radians, I mean, it's not really a big deal either way. But any ideas on what we can say about this? So again, you can take your intuition from, again, limits, improper integrals, sort of the same sort of strategy. You see an absolute value around a cosine squared plus 1. What do you think?
It's not really necessary because cosine squared will always be positive.
Okay.
And in the bottom, there's an n squared plus 1, and that'll also never be negative.
Okay. So, I mean, so you're saying that we just get the original. Okay. Is that what you're saying?
Yeah.
This is true. However, it's not helpful to notice that. It's actually more helpful with the absolute values, believe it or not.
Well, since it's always positive, sorry, can you hear me?
Yes.
Okay. I don't know. Is that it looks like it's always decreasing as well? So could we do the integral test and make cosine squared n plus 1 into sine squared n, and do like a
cosine squared n plus 1 is not sine squared. Also, the integral test, no, we don't know how to integrate that.
Okay.
What technique would you use? Like a cosine squared over n squared plus 1.
Did you try the ratio test? And see if you can get like the cosines to cancel at any point?
You would get, yeah, well, the plus 1. And also, you don't really know how a cosine squared of n plus 1 would behave in relation to a cosine squared n. I mean, think back limits. Like you see a trig function in absolute values, you're supposed to have a knee-jerk reaction from that. Like cosine, like whatever, like it's a cosine. If I put it in absolute values, what is the first thing you think?
it's between 0 and 1.
It's between 0 and 1, right? You automatically start thinking of bounds, right? Yeah. What can we do here in that regard? I have an absolute value of a cosine squared plus 1. How can I bound that?
It'll be between 1 and 2.
Right, the numerator is going to be between 1 and 2. In particular, it's going to be less than or equal to that, right? Okay, what can you tell me about that new series, which is a lot easier to deal with than the cosine squared in that series?
Isn't that just a P series, or is that what it's called?
Not quite a P series because of the plus 1.
Oh.
But yeah, you can see that a P series is clearly something it's close to. So what would we want to do?
you can compare it to a.
You want to compare it to a
P-series.
P-series. What P-series would you want to compare it to?
Doesn't matter like what the numerator is, like 2 over n
2 over
squared.
n. What would that be? Would that be bigger or smaller?
Smaller.
It has a
because
it has a smaller denominator, so it's a bigger fraction. So it goes this way,
Oh yeah.
right?
Yeah.
And what can you tell me about this one? This here is a convergent P-series.
And yeah, by that theorem, the smaller one, which is the
This
series that we were
means
looking at convergence.
this guy converges, right? By what? What did we just do? What is that thing called that we just did?
Comparison.
By comparison. In fact, it has absolute values around it. So we can even say a little bit more than this. What kind of convergence did we just observe?
Absolute.
We observed absolute convergence, right? Because it converged with absolute values around it. So I can say, yes. So I can say something like, let me leave this here and I'll just say it later on. This means that the original series converges absolutely. I can say by the comparison test. Right? So notice here, this process terminated at step 1. Step 0 was inconclusive, so I moved down to step 1, and I found convergence at step 1. So I stopped, right? So in this table, right? I tried the test for divergence, it was inconclusive, so I moved to step 1. And then I check if this converges, and it did. So I stopped and I said, the series converges absolutely by whatever test I used, right? Hit it with test for divergence, inconclusive. Move down, check absolute convergence. Put absolute values around it. Sometimes this should kind of hint to you what you should do. You see absolute values around a trig function, you're automatically should be thinking of some bounds, right? At least if your Calc 1 professor drilled into that idea into you correctly. So you see a sine or a cosine inside absolute values, you automatically start thinking, oh, there's like a 1 over here and a -1 over there. If it's square, there's a 1 over here, there's a 0 over there. So it automatically just starts to play an inequality into your hands, which then makes you automatically think of things like a comparison theorem, because comparison theorems are the ones with the inequalities, right? And so, yeah, I just keep going to compare. By the way, here we could have showed that this converges by the integral test, but that of course would be more work. But it was also an option. You can say this is less than this, and this one converges by the integral test, because the integral of this is arctangent to arctangent of n, and as n goes off to infinity, that would go to pi, and as n goes to 0, that would go to 0. So this guy actually converges to pi under the integral test. The corresponding improper integral converges to pi. So we do know by the integral test this converges, but that's actually more work than just getting rid of the +1 in the denominator and comparing it to a P-series. But there are tons of different ways, which is why you should be identifying what you're doing. So you know what you're doing. I know that you know what you're talking about, and I can see whether you're thinking as efficiently as possible or not. Okay. So that's the first example. Let's go on to the, yes?
Sorry, can I just ask real quick how you went from, I understand like the bounds and everything, but how you got to what you rewrote as 2n squared plus 1 from computing the bounds of the cosine?
Well, because I know that cosine squared is between 1 and 0. So this means that my cosine squared n plus 1 is going to be between, if I add 1 on both sides. And so that automatically tells you that cosine squared plus 1 is less than 2 in absolute values.
Okay.
Right? So the maximum the cosine squared part can be is positive 1. And so the maximum this can be is 1 plus 1, which is 2. And so I have that. Okay, here, same question. Does this converge absolutely, conditionally, or diverges? Ideas?
So the function n factorial over n to the n itself
Yes,
converges to 0.
right? So
So the function would converge to -1 to the n cosine of 0, which is
cosine
1.
of 0. Cosine of 0 is 1. So in fact, you can actually show. So boom, hit it with a test for divergence. So what I do is I go for the limit of an, which, by the way, I can ignore the plus or minus 1. So can ignore the minus 1 to the n, since if I have minus 1 to the n times 0, then that's just going to give me 0, right? The sign of the 0 is not, if it actually hits 0, right, the sign of the 0 is not going to matter, right?
Wait,
so I can actually just...
Isn't it going to hit 1 and not 0?
Right. So I'm saying in the case where I wouldn't be able to make a conclusion, me leaving off the sign is not going to work anyway. And in the event that it doesn't hit 0, then whether or not I hit a plus or minus a non-zero number also won't matter, right? And minus 1 to the n of k, where k is not 0, is also not 0. Right? So whether or not I would get 0 or non-zero is not going to be affected by the sign. So I can just ignore the sign. Right? If I get a 0, I don't care if it's a plus or minus. And if I don't get a 0, I don't care if it's a plus or minus, right? I just care 0 or not, right? If it's not 0, whether it's positive or negative doesn't matter. It's diverges. If it is 0, whether it's positive or negative makes no difference whatsoever. So I can just ignore the sign altogether. And that, as you rightly said, approaches cosine of 0, which is 1, which in particular is not 0. Therefore, what can I say?
It diverges.
Yeah, the series diverges. You don't have to do anything. And you can say if you want by test for divergence. And you stop. You don't have to do anything else, right? You don't have to check conditional. You don't have to check absolute. It diverges just right off the bat. Once this thing doesn't hit 0, it doesn't matter if I put absolute values or not. It's never going to work, right? Which is why a test for divergence is nice. Like some of you just saw, like just by looking at it, that's not going to 0, right? So you can make a quick deal of this. Same question. Converges absolutely, converges conditionally, or diverges. So we know the strategy. Step 0, try the test for divergence. So we find the limit of an. That's going to look like the limit of n over n plus 1 to the n. Okay, what is that?
One, which is not 0.
It's not 1.
Wouldn't you get 1 to the infinity, which is an indeterminate form?
Right. This approach is 1 to the infinity, which is indeterminate.
Quick question, why is that indeterminate? Like, why doesn't it equal 1? Because it looks like it would.
Well, to answer that, we can actually just finish this example because this does not converge to 1, and you're going to see that it doesn't. Which is particularly why it's indeterminate, because we know for a fact that it doesn't always converge to 1. So it's not clear. That's why it's indeterminate. You can't take it at face value. I'll tell you the short way to do this. Notice that this is the same as the following. I flip it and put it in the reciprocal. Do you guys see it? We go a little further. That's that. Do you guys see it now?
Isn't that 1 over e?
That's 1 over e. So that's the definition of e was hidden in here. So it's actually not 1. Now, of course, it's not 0, so it still diverges, but it's actually not 1. So yeah, the series diverges. Now, you might be worried that, oh man, I'm never going to remember the definition of E, and you should. So I went over this with you guys in that general office hours, that you should always remember the definition of E. Always remember. It'll pop up in the weirdest places, trust me. Okay, so you should always remember the definition of E in all its forms, because it'll show up, and you'll see it hidden in various places. Now, for whatever reason, maybe you were just slow on test day, but you're kind of out of it, so you didn't notice this. Let's go back alternatively. Yes. How would you have done this if you didn't see that there was an E there? You notice that this is 1 to the infinity. What do? In fact, you notice that the power is a problem. What do you want to do when a power is a problem?
Take the natural log.
You want to take natural logs, right? Now, a couple ways you can approach this. You can set this limit equal to some other variable, say y equals this limit, and you can log both sides and rework. But you can also rewrite on the spot, which is, for problems like this, is probably what I would recommend in general. You can write it as e to the ln of the thing. And that's where the E would come from. That allows you to get rid of the power. When you know an exponent is a problem, logs help you with that. Logs cancels exponents. So now I would have the limit of E to the n ln of n over n plus 1. Notice that now the power would approach as n is approaching infinity. It approaches infinity times, as n approaches infinity, that approaches log of 1, which is 0, and still indeterminate. Right? You can't tell that at face value. So you have to do something like rewrite. So you can rewrite this as something like ln of this over, say, 1 over n. Then you would notice that this goes to 0 over 0, which means that L'Hopital's rule would apply. And so you can actually take the derivative of the top, derivative of the bottom. So that's going to be 1 over n minus 1 over n plus 1, all over minus 1 over n squared. And that would look like did I do this correctly? I think in my head, what was I doing? I think I thought of that as ln of n minus ln of n plus 1 in the top, differentiated each part. Let's keep, I think I probably want to rewrite this a little bit nicer, but let's think of it like this. Bring in the n squared. Let me combine these. N plus 1 minus n, or n squared plus n. All right, so that gives us e to the minus 1 after taking the limit. So again, that's non-zero, right? So L'Hopital's rule is a way you could get around it, but it would take much longer if you didn't see the definition of e. That's much shorter if you saw that. Much nicer, much more elegant. So you see something like an n over an n plus 1 to an n, you would often think of that as, oh, that's kind of e upside down. Or if you see the n plus 1 all over n to the n, you can also interpret that as e. Or obviously the 1 plus 1 over n to the n. That's how we're used to seeing it. So when I rewrote it that way, that's when you guys saw it. But don't underestimate being able to see e in these forms as well. Can be very useful. Anyway, at the end of the day, test for divergence says this diverges. And you can either notice that very quickly if you saw the definition of E, or you can take a very long time to notice that if you didn't see the definition of E and remember things like L'Hopital's rule. Was that the third example? Yeah. Wow. So far, for the first one, we had absolute convergence where the test for divergence was inconclusive. Here we had the test for divergence tells us it diverged right away. Here, test for divergence tells us it diverged right away. Let's see what we have here. So here's another one. And as always, we're going to hit it with a test for divergence. Test for divergence says I can find the limit of an. That's just the limit of 1 over ln of the square root of n plus 1. What is that?
Zero.
That's 0. What does that mean?
Inconclusive.
Inconclusive. All right, so next, we're going to check for absolute convergence. What does that mean? We are going to take our series and we're going to put absolute values around it, which basically means this guy is going to behave more like a 1 over ln square root of n plus 1. So we're going to consider this guy. Okay, so now our focus is on this guy. Tell me about this guy. Converge or diverge? By the way, you can notice that I have ln of a radical. I can think of that radical as a half power, and I can bring that half power down. So this guy is actually the same as that. Tell me about that guy. Converge or diverge, and how do you know? Any ideas? Can look back at the series test. Which one would work out nicely here? We're actually going to talk about this after. Okay, so at least respond to me here. Let me see if we're still breathing. Okay, is this a geometric series?
No.
No. Yeah, nah. Would you want to do the integral test on this?
Not really.
Not really, right? Like you can't even, like, I can't even fake it. If there was a factor of an n plus 1 in the bottom, that would definitely be an option because then I could do a substitution. But integrating 1 over ln of x? No, that doesn't seem like it's going to work out. So yeah, probably not. What else? Ratio test? Do you think the ratio test would work? What do you think would happen if we did the ratio test?
I'm not sure what would happen, but I don't think it would work.
Would we get 1?
You would get a 1. Right. So remember the ratio test is going to take an plus 1 divided by an, right? So you're going to end up with something like ln of n divided by an ln of n plus 1 as n is going off to infinity. That approach is 1, which means that the ratio test would be inconclusive, which automatically means that the root test would be inconclusive. So not geometric, don't want to use the integral test, can't be a ratio test because that's inconclusive, can't be a root test. What do we have left?
Comparison.
Alternating series, but that doesn't tell us if it's absolute convergence.
Come again?
Well, the original one.
Yeah, but remember, we are in this phase. We're checking absolute convergence. So we're not allowed to go there. This is the focus now, this guy. I am the captain now. Right? This is your focus, right? It's not alternating, so you can't use the alternating series test. What else is there?
Could you compare it to something?
Comparison, right? Like almost nothing else we worked. Okay, so now you're like, okay, comparison, because what else is going to do? I can't use the alternating series test. Ratio test and root test inconclusive. It's not geometric. Integral test, forget about it. What are you going to do? If you have a series where it's like, it's very complicated to work with in general, why not compare it to something easier to deal with, right? Okay, so comparison is the idea. Now the $1 million question, what do we compare it to?
This is probably wrong, but couldn't you compare it to, shoot, what is that, 2 over x? Or n, sorry, n? Because doesn't that grow faster than ln n? Maybe.
A very good thought process. I wouldn't go all the way to n though, but yeah, I would compare it to 2 over n plus 1. Right? And why? Because remember, we have that idea, right? That the logs grow less than polynomials, which grow less than exponentials, which grow less than factorials, which grow less than this guy, right? So log to the base a, right? So this kind of tells you that ln of x is going to be less than x as you're going off to infinity. And this should be clear, right? You can have your ln of x like that. That's your ln of x. And then your x is this guy. In other words, the x is always going to outgrow ln of x. So you can always compare ln of something to the thing inside the ln. The thing inside the ln is going to be, of course, if we're assuming that it's always positive, the thing inside the ln is going to be bigger. ln makes things smaller. It'll take a line like this and it'll curve it down like that. It'll start to shrink the bigger values. So I could actually compare it to that. And in fact, I would know now, because my n plus 1 is larger than my ln, what can you say about this? What direction does this go in? Which one of these series is bigger? The top one or the bottom one?
Top one.
The top one is bigger because it has a smaller denominator. So this goes that way. Now, what can you tell me about this guy? Two over n plus 1. Converge or diverge?
Diverge by the integral test.
You can diverge by the integral test because if you integrate that, you get 2 ln of n plus 1 as n goes off to infinity. Ln of infinity goes off to infinity. You can also notice that it diverges because it's actually a p-series. Now, I know it does look like a p-series because of the plus 1, but it's actually literally the p-series. Like, notice that if you set, say, k equals n plus 1, then you get the series 1 over k, well, of course, times 2, with k starting from 2. K equals n plus 1. Probably want to actually shift this first. So I would say something like diverges, it is a p-series. But I have to be careful. I don't want to divide by 0. It's a p-series. How do I know? Like if I go from 1 to infinity of 2 over n plus 1, this is going to be equal to, when I plug in n equals 1, I would get 1 plus, then I can start this from n equals 2, 1 over n plus 1. If I set k equals n plus 1, then this would mean, I think it was fine the other time, because k minus 1. Then this would mean I have 1 over k here, and then I would start at k equals 3. It was fine before. It was just adding in my head when I should have been subtracting. So it starts from k equals 3. This is actually equal to too frazzled today. So here, n equals 1. If I set k equals n plus 1, this means that my n is equal to k minus 1. So I go everywhere here and plug in k minus 1 for all my n's, and I would end up with 2 over k. K goes from 2 to infinity, and that's harmonic. So it's a harmonic p-series. Also, integral test. So there are various ways that you can see it. You notice that 2 over n plus 1 is greater than 0, decreasing, and continuous on 1 to infinity, and the integral from 1 to infinity of 2 over n plus 1 dn is going to be equal to 2 ln of n plus 1 between 1 and infinity, which equals infinity, so it diverges. So a couple different ways. I could do a limit comparison with a p-series. I could limit compare this with 1 over n. I could notice this little just by shifting 1 over. It's literally just a shifted version of 1 over n if I write it in the version of 1 over k or whatever, right? So tons of ways you can do this. But at the end of the day, you should be able to recognize that that series diverges in pretty quick order. Making the jump of knowing that you want to compare the 2 over ln of this thing to just 2 over the thing, that's a little bit more conceptual, but now that I've shown you this strategy and I explained it, it should be something that you should be able to pick up on quicker in the future. So now what do we have? So this means the series does not converge absolutely. By comparison. I know that because this guy diverged and he is smaller than that guy up there. So when the smaller series diverges, the bigger series will obviously diverge. So now we're in a situation where the test for divergence was inconclusive. I move down to check for absolute convergence. That doesn't work out. So now I'm in the other step. So here, now I'm in step 2, check conditional convergence. What does that mean? It means I go back to the original series without the absolute values. All right, what can you tell me about this series? Converge or diverge?
Converge by alternating series.
Right, so note AN equals 1 over this is positive. It's decreasing, obviously, and the limit of AN equals 0. Therefore, the series converges. And now I can classify it conditionally. By the alternating series test. It's also possible at this stage to find that even this didn't work out, it diverged, and in which case you would conclude that it diverges. But yeah, this is an example of a problem where we have to go through all the steps. So you hit it with the test for divergence, but it was inconclusive. So then you check absolute convergence. Put absolute values around it, figure out if it converges. In this case, comparison theorem was the easiest one to hit it with, so I did that. And then it showed divergence with the absolute values. So then what I do is I take the absolute values back and try to get away with conditional convergence. So absolute convergence was the gold standard. It was our hope. Didn't work out. So let's see if we can escape with conditional convergence. And in this case, we can check for conditional convergence. The -1 to the n screams out alternating series test, and this converges by the alternating series test. However, it did not converge absolutely, which means it converges conditionally. So this is what converges conditionally means. Means when I put absolute values around it, it didn't work. But when I took them back, now suddenly it works, right? So it doesn't work with absolute values. It works without them though. So this is what you call a conditionally convergent series. So this series here converges conditionally. This series here diverged. This series here diverges. And this series here converge absolutely, right? So now you can determine whether or not series are converging absolutely, whether they converge conditionally, whether they just diverge altogether. So you can do all sorts of tricks here. But we sort of was going through this game, and I slowly let you guys go through the painful process of actually trying randomly, desperately for a strategy to use. But hopefully you were picking up some lessons along the way, certain things that you noticed that you would look for. And hopefully me questioning you in the way I did also kind of helped you. So if you look at something you don't know, worst case scenario, right? You just start at the top of the list. Could it be geometric? Could I use a p-series? Could I use a comparison test? Could I use the integral test? And you basically can figure out by process of elimination what would work versus what doesn't, assuming you have the math skills to pull it off. It's another story if you think something can integrate when it can't, right? That's something that hopefully after chapter 7, you're not going to fall into that mistake, right? So you realizing that 1 over ln of something, you can't integrate it, that's what made you think of something else, right? But yeah, so those are all the examples here. That being said, let's actually do this. Let's actually figure out how to be more efficient with this. So similar to what we did for integrals, I'm going to do for series. I'm going to give you a strategy of how you're going to tend to want to apply the series tests. So let's talk about how to approach series convergence problems. So I give you a problem, I ask you, does this series converge? And I may ask you, does it converge absolutely? Does it converge conditionally? Does it diverge, right? I can ask you this at multiple levels, whether a series is converged. How do you know what to do? In the same way, just as before, when I gave you this random integral, compute this integral, how do you know what method to choose? How do you know, do I do substitution? Do I do that by parts? Do I do something else, right? Series has a very similar challenge to it. There are multiple methods and you just have to pick the one that's most efficient or that would work at all, is the challenge, right? Now, any one particular one, when you're applying it, it shouldn't be difficult to actually apply it once you see which one you want to use, which one is appropriate to use. But seeing it tends to be the hardest part. Another thing with series is certain misconceptions that tend to creep up. So we tend to mix things up with limits, and we tend to think of things like the limit converging meaning the series converges, which is not true. I actually asked that in a quiz already. Or another misconception is when someone tries to test for divergence and they see it hits 0, a lot of students just fall into the trap of thinking that that means convergence when it does not. So aside from the misunderstandings and just not paying attention to what the theorems say, the biggest issue should be recognizing what series test to use. So let's actually get that out of the way. Yeah, so general approach to series. How do I know what series test to use if I want to figure out convergence? Well, step 0 is always to try the test for divergence. Find the limit of an. If it's not 0, it diverges. Easy peasy. If it is 0, do not assume it converges. It is inconclusive. Right, so let me write that here. Limit of an not equals 0 means diverges. Someone got kicked out. Let me put them back in. Limit of an equals 0 means inconclusive. Do not fall into the trap of thinking that you can make a conclusion from that. You cannot. Okay, so you hit it with test for divergence. That's step 0 before you do anything. Kind of like when you randomly approach limits in Calc 1, one of the first things you check is, can I plug in the number to find the limit? And then you try something more sophisticated. Step 0, if a problem specifically asks you to what something converges, right? Like I don't say the series converges. I say something like the series converges, find its value, or evaluate the series, or what does this converge to? Then you're actually in pretty good company because there are literally only 2 situations in which a Calc 2 student would know how to find the exact answer off the top of their head. And one of those situations we didn't even do, which is the telescoping series. So you literally only have one situation. So if I ask you, what does a series converge to? It's literally always one thing, the geometric series. We know that when a geometric series converges, we know specifically that it converges to a over 1 minus r. So if I ask you specifically what it converges to, then if you find that it converges, it's probably geometric. Just do the geometric series test. That's just a hint. Step 000. If I ask you about absolute versus conditional convergence, you need to use the method that I told you in the previous, the end of the last section, right? So we're still doing series tests, but you're doing it within this structure. Test for divergence, test absolute convergence, test conditional convergence. You stop whenever you can make a conclusion, right? So those are just the preliminaries, right? These are the first 3 things you always think about. The next few steps is in no particular order. It just depends on what the series looks like. Okay, so here are some things that you should notice. See if your series has a specific form. There are a bunch of series with specific forms, right? The geometric series is one of them. It has a very specific form, a times r to the n, or a times r to the n minus 1. It must look like a constant times a constant to the nth power, right? Or an alternating series has a very specific form, -1 to the n of an, right? A p series, very specific form, 1 over n to the p. So you are faced with a random series, provided that the test for divergence doesn't work out, and I didn't ask you exactly what it converges to, and you don't really care if it converges absolutely, conditionally, or whatever, then look for a specific form. There are a bunch of series in the table where it requires a specific form to apply. And remember with this one, alternating series test can only determine conditional convergence. So just, you need to be aware of that. But otherwise, it's pretty clear. If I see a series like one of the first two, geometric series test, obvious. If I see like the third series, alternating series test, obvious. Unless I'm asked about absolute convergence, then no. If I see a series like 1 over n to the p series test, obvious. Why? It has the right form. Here's a second scenario. If your an is a rational function, or it's close to being a rational function, a comparison test is going to be useful. Comparison is also useful when you realize that you need to just simplify things when you're completely lost. Like the 2 over ln of the radical, but like, what the hell? Like, I don't know what to even do with this. Whenever you're in that situation, you probably want to compare it to something that you do know better how to deal with, right? So comparison is like a last this effort, when it's like, this thing is too complicated for me to do literally anything with. Let me compare it to something easier and figure out what's going on with that guy. Then you want to think comparison or limit comparison. Otherwise, guys that are a dead giveaway for comparison are rational functions, like this guy, right? Obviously, you'd want to compare to, well, just focus on the highest powers. So you'd want to compare to something like 1 over n, right? Because you'd compare it to n squared over n cubed, right? This guy, again, if you focus on the highest powers, this is not rational, but this is what I mean by close to rational. It means in its limit form, it behaves like a rational function. In its limit form, I can compare it to, if I just ignore all the lower powers, this guy is going to look like an n squared over a radical n to the 8, which looks like an n squared over an n to the 4th, which behaves like a 1 over n squared. So I would actually compare it to that. So if it's rational or is very close to being rational, comparing it to a p series is very often going to work. Otherwise, you'd probably think comparison if the function is just too complicated. The ratio test doesn't work and it's just complicated to apply. The integral test doesn't work, complicated to apply. Doesn't have a specific form that I can take advantage of. It's not geometric, nothing. Then chances are you want to compare it to something, right? So that's when you would think comparison theorem. If it includes factorials or a lot of exponentials, you might want to try the ratio test, right? We saw last time that when you had factorials, taking the ratio allows you to cancel off a lot of the common factors. So you can simplify things very nicely with the ratio test. So ratio test comes in very nicely when you tend to have factorials and things of that sort, or maybe exponential functions that aren't geometric. Then the ratio test might work. Not all the time, but it would be something that you would think about. Our example of n over n plus 1 all to the n, the ratio test was inconclusive there. But with something else, it might not have been. So yeah, you'd think the ratio test with things that have variable powers, but they're not geometric, or if they have a bunch of factorials, the ratio test is worth considering. Also, you need to remember that the ratio and the root test will make similar conclusions. Meaning, if you try the ratio test and it's inconclusive, do not try the root test. The root test is also going to be inconclusive. The ratio and root test will make very similar conclusions. So if one doesn't work, the other one is not going to work. So once you use one of these guys and you get to a conclusion, you don't need to check anything else. And if one of them is inconclusive, the other one is going to be as well. So you don't want to you very rarely need to use both of those tests. So if you use one of these and it's inconclusive, use another test from the table. Whenever you have something to the nth power, specifically, you just have an nth power. You just have an nth power. Or maybe sometimes it can work with a power that's a constant times n, where you can just like factor off an nth power. The root test would work there. So I would try the root test in this scenario, right? Because then I take the nth root, which gets rid of the nth power, right? It helps me to simplify a little bit. Again, it doesn't always work with the same example, n over n plus 1 all to the n. Take the root, I would just get n over n plus 1. The limit is 1. Inconclusive, just like with the ratio test. They'll always behave very similarly. If I can think of my an as a function, and I realize that that function, hey, that looks like something I could integrate easily. I mean, it's very complicated otherwise, but as an integral, it's easy, right? So we saw an example of this, something like a e to the 1 over n squared, right? Looks like a very complicated thing, but I can integrate that pretty easily. U equals 1 over n, and the integral is nice. Then just make sure that you do check these guys have to work. So it has to be continuous, has to be positive, has to be decreasing. And that's basically it. So that's how you'd actually go about the strategy. It's a 5-step strategy for series overall. Comparison theorem is probably the comparison theorems, limit or direct, are probably the last ditch efforts. Like when you really have no clue what's going on, compare it to something easier. But if you have something like rational or close to rational, that's kind of a dead giveaway that you want to go to comparisons. So again, test for divergence, always the easiest thing to see and quickest thing to apply, so check it out. If it's geometric, or I ask you specifically what something converges to, then it has to be geometric, like there's nothing else. If I see that the series has a specific form, like a geometric or alternating or p-series, apply those as long as I don't care about absolute convergence. Try comparison tests if you don't know what's going on, or it's almost rational or it is rational. If you see a lot of factorials or weird exponentials, think the ratio test. If you see an exponential where the power is n or a constant times n, try the root test. Notice that both of these will be inconclusive at the same time. If it looks like something you can easily integrate, try the integral test. And again, you can double up on these tests. So maybe you compare it to something and then realize that, hey, that is easily integrable. I can just do the integral test on this comparison. Then you can go that way as well. So that's kind of like the approach. So first thing, you just have to know all the things in these table. Here's when you're allowed to use it. Here are the conclusions you can make. And as for a strategy, when you might think to use which test, I just told you. So that looks like a good place to end it here. Next time, I'm going to talk about estimating series and power series, I believe, are the next ones. So very interesting topics. That's when we start to do a lot of, we get into starting to do applications with series. So that should be pretty fun. But yeah, that's all I have for you. So I'll give you the notes here. I might also post the notes for estimating series. You can read through this. It should be something that you could figure out on your own. Just do this example here. And yeah, we will start there. We will stop there. So that's how you approach, that's the strategy. Hopefully that was helpful. Go back and practice. Just like with integrals, series, it's going to take a lot of practice of you knowing what to apply. So the same principles I told you about integrals, how to get good at integrals, you're going to apply the same thing again. So you're going to go to your textbook, you're going to find the section where all the series are, you're going to do a bunch of them. And then eventually, you're just going to start pointing at random series. Give yourself 5 seconds to figure out the approach, right? You shouldn't need more than that. If you need more than that, it means you don't know it well enough and you need to keep working. Yeah, we'll stop there. thank you for your attention. Thanks for staying a little bit later. I know I have office hours with one of you, so I will go to that. In the meantime, everyone else, have a good night. Have a good weekend. I will see you guys in the next one. Ciao.